The Chernobyl Nuclear Power Plant or Chornobyl Nuclear Power Station is a decommissioned nuclear power station near the city of Pripyat, Ukraine, 14.5 km northwest of the city of Chernobyl, 16 km from the Ukraine-Belarus border, and about 110 km north of Kiev. Reactor No. A4 was the site of the Chernobyl disaster in 1986 and the power plant is now within a large restricted area known as the Chernobyl Exclusion Zone. The nuclear power plant site is to be cleaned by 2065. On January 3, 2010, a Ukrainian law stipulating a program toward this objective came into effect. Construction. The V.I. Lenin Nuclear Power Station, as it was known during the Soviet times, consisted of 4 reactors of type RBMK 1000, each capable of producing 1,000 megawatts of electric power, and the 4 together produced about 10% of Ukraine's electricity at the time of the accident. The Chernobyl station is 18 km northwest of the city of Chernobyl, 16 km from the border of Ukraine and Belarus and about 100 km north of Kiev. Construction of the plant and the nearby city of Pripyat, Ukraine to house workers and their families began in 1970, with Reactor No. 1 commissioned in 1977. It was the third nuclear power station in the Soviet Union of the RBMK type, and the first ever nuclear power plant on Ukrainian soil. The completion of the first reactor in 1977 was followed by Reactor No. 2, No. 3, and No. 4. 2 more reactors, NOs 5 and 6, capable of producing 1,000 MW each, were under construction at the time of the accident. Reactor No. 5 was about 70% complete at the time of the accident and was scheduled to start operating on November 7, 1986. However, the works were halted on January 1, 1988, leaving most of the machinery behind. Furthermore, a 6th reactor was planned in a new block of buildings scheduled to be completed in 1994. Reactor NOs A3 and 4 were second-generation units, whereas NOs A1 and 2 were first-generation units. Second-generation RBMK designs were fitted with a more secure accident localization system, as can be seen in pictures. It is fortunate that the accident happened in a second-generation unit. If it had happened in a first-generation unit, it could have been even more devastating. Today, many countries that were in the Soviet Union have been forced to shut down such first-generation units by the European Union, as they pose a threat to the environment. Electrical systems. The power plant is connected to the 330 kV and 750 kV electrical grid. The block has 2 electrical generators connected to the 750 kV grid by a single generator transformer. The generators are connected to their common transformer by 2 switches in series. Between them, the unit transformers are connected to supply power to the power plant's own systems. Each generator can therefore be connected to the unit transformer to power the plant, or to the unit transformer and the generator transformer to also feed power to the grid. The 330 kV line is normally not used, and serves as an external power supply, connected by a station transformer to the power plant's electrical systems. The plant can be powered by its own generators, or get power from the 750 kV grid through the generator transformer, or from the 330 kV grid via the station transformer, or from the other power plant block via 2 reserve push bars. In case of total external power loss, the essential systems can be powered by diesel generators. Each unit transformer is connected to 2 6 kV main power boards, A and B, powering principal non-essential drivers and connected to transformers for the 4 kV main power and the 4 kV reserve push bar. The 7A, 7B, and 8B boards are also connected to the 3 essential power lines, each also having its own diesel generator. In case of a coolant circuit failure with simultaneous loss of external power, the essential power can be supplied by the spinning down-to-bowl generators for about 45–50 seconds, during which time the diesel generators should start up. The generators are started automatically within 15 seconds at loss of off-site power. Turbo generators. The electrical energy is generated by a pair of 500 MW hydrogen-cooled turbo generators. These are located in the 600 am long machine hall, adjacent to the reactor building. The turbine is the venerable 5-cylinder K500-65/3000 are supplied by the Kharkiv turbine plant. The electrical generators are the TBB500. The turbine and the generator rotors are mounted on the same shaft. The combined weight of the rotors is almost 280 and their nominal rotational speed is 3000 rpm. The turbo generator is 39 am long and its total weight is 1280. The coolant flow for each turbine is 82,880 ATH. The generator produces 20 kV 50 Hz AC power. The generator's stator is cooled by water while its rotor is cooled by hydrogen. The hydrogen for the generators is manufactured on-site by electrolysis. The design and reliability of the turbines earned them the State Prize of Ukraine for 1979. The Kharkiv turbine plant later developed a new version of the turbine, K500-65/3000-2, in an attempt to reduce use of valuable metal. The Chernobyl plant was equipped with both types of turbines. Block 4 had the newer ones. The newer turbines, however, turned out to be more sensitive to their operating parameters, and their bearings had frequent problems with vibrations. Reactor fleet, 4 MBK reactors were at Chernobyl, NPP. Chernobyl 3 performed a total power loss test like the kind that caused the accident at number 4. Reactors number 1-3 continued to operate until their shutdown in the 1990s. Number 5 number 6 were cancelled while partially complete. Accidents: 1982 Reactor number 1, on September 9, 1982, a partial core meltdown occurred in Reactor number 1 at the Chernobyl plant. The extent of the accident was not made public until several years later. The reactor was repaired and put back into operation within months. 1986 Disaster Reactor number 4. On Saturday, April 26, 1986, a disaster occurred at Reactor number 4, which has been widely regarded as the worst accident in the history of nuclear power in the world. As a result, Reactor number 4 was completely destroyed and is being enclosed in a concrete and lead sarcophagus to prevent further escape of radioactivity. Large areas of Europe were affected by the accident. The radioactive cloud spread as far away as Norway. 1991 Fire Reactor number 2, the Chernobyl nuclear plant utilized one large, open turbine hall for all 4 reactors without any separating walls. Each reactor had 2 turbines. On October 11, 1991, a fire broke out in the turbine hall of Reactor No. A2. The fire began in Reactor No. A2's turbine E4 while the turbine was being idled for repairs. A faulty switch caused a surge of current to the turbine, igniting insulating material on some electrical wiring. This subsequently led to hydrogen, used as a turbine coolant, being leaked into the turbine hall, which apparently created the conditions for fire to start in the roof and for one of the trusses supporting the roof to collapse. The adjacent reactor hall and reactor were unaffected. Ukraine's 1991 independence from the Soviet Union generated further discussion on the Chernobyl topic, because the Rada, Ukraine's new parliament, was composed largely of young reformers. Discussions about the future of nuclear energy in Ukraine helped move the government toward the political decision to cancel the operation of Reactor No. A2. 2013 collapse. On February 12, 2013, a 600-square-meter portion of the roof and wall adjacent to the covered part of the turbine hall collapsed into the entombed area of the turbine hall. The collapse did not affect any other part of the object shelter or the new safe confinement. No variances in radiation levels as a result of the incident were detected. The roof which collapsed was built after the Chernobyl disaster. Plant shutdown and decommissioning. After the explosion at Reactor No. 4, the remaining 3 reactors at the power plant continued to operate. In 1991, Reactor No. 2 suffered a major fire, and was subsequently shut down. In November 1996, Reactor No. 1 was shut down, followed by Reactor No. 3 in 2000. This would normally require several years, but the complication of Reactor No. A4's explosion and current state has already extended the time required, and will continue to do so for many years more. The first stage of decommissioning is the removal of the highly radioactive spent nuclear fuel, which is placed in deep water cooling ponds. However, storage facilities for this are not suitable for long-term containment, and those on site do not have the capacity for all the spent fuel from reactors 1, 2 and 3. A second facility is planned for construction that will use dry storage technology suitable for long-term storage and have the required capacity. The schedule for plant decommissioning is intimately wrapped with the dismantling of Reactor No. A4 and the decontamination of its environs. The Chernobyl new safe confinement will have equipment which will make decommissioning relatively incidental to, yet an integral part of, the cleanup of the exploded reactor. The Chernobyl nuclear power plant had no reactors left to run the turbines, so the generators could not run. Removal of uncontaminated equipment has begun at Reactor No. A1 and this work could be complete by 2020-2022. The remains of Reactor No. A4 will remain radioactive for 1,000 years. The isotope responsible for the majority of the external gamma radiation dose at the site is cesium-137, which has a half-life of about 30 years. Thus the radiation exposure from that radionuclide has almost declined to half of the original value right after the explosion. It is likely that with no further decontamination work the gamma-ray dosage at the site will return to background levels in about 300 years. However, most of the alpha emitters are longer-lived, and the soil and many surfaces in and around the plant are likely to remain contaminated with fuel and transuranic metals such as plutonium and americium, which have much longer half-lives. It is planned that the reactor buildings will be disassembled as soon as it is radiologically safe to do so. It is hoped that future technologies will help make cleanup of those materials feasible without having to await their long decay. Sarcophagus replacement. Originally announced in June 2003, a new steel containment structure named the New Safe Confinement would be built to replace the aging and hastily built sarcophagus that currently protects Reactor No. A4. Though the project's development has been delayed several times, construction officially began in September 2010. The new safe confinement is financed by an international fund managed by the European Bank for Reconstruction and Development, is being designed and built by the French-led consortium Nvalca, which includes the companies Bouygues and Vinci. Nvalca is building a giant arch-shaped structure out of steel, 190 am wide and 200 am long to cover the old crumbling concrete dome that is currently in use. This steel casing project is expected to cost $1.4 billion, and expected to be completed in 2015. A separate deal has been made with the American firm Holtk to build a storage facility within the exclusion zone for nuclear waste produced by Chernobyl. The shelter replacement required demolition of the iconic 75-meter-tall exhaust chimney which was used for both reactors number 3 and 4. A shorter stack has been constructed adjacent to it that will be used to ventilate the new shelter. See also. References. External links. Chernobyl Nuclear Power Plant official website English icon on homepage, Chernobyl Nuclear Power Plant at Google Maps, steel sarcophagus announcement. A zone virtual walk with comments by Natalia Monasternier.